Okay. Well, I'm really happy to be talking to this audience. I came here more to learn than to teach, but I hope I can tell you some things that maybe you don't know, especially about Haskell. Probably not about C++ so much. So this will be a three-part talk. So like the middle part will be split between two segments. The first one is sort of an introduction both to Haskell and a refresher on template metaprogramming. So why Haskell and C++? These seems like complete opposites, right? I mean, Haskell is this functional, pure, elegant language, and C++ is like the opposite of that, right? I know, we love C++. Only like a mother can love an ugly child. Right? But it's amazing that actually the same ideas, the functional ideas from Haskell, are getting into C++, and actually, like at the forefront of this movement was always, Boost was always at the forefront of this movement. Not so much as well, both at runtime, using lambdas, and at compile time, using metaprogramming. There was always a very strong functional aspect to it. So why Haskell? Why do I want to talk about Haskell at all? It has easy syntax because it's a single paradigm language. It's just functional language, nothing else. So since it has only one paradigm to support, the syntax is really easy and very, very terse. So it takes some getting used to it, but once you get used to it, it's really, you can read Haskell without problems. There's almost one-to-one match with C++ template metaprogramming. This is pretty amazing because if you try other functional languages like ML, they don't really translate that easily. But Haskell is like perfect match. You have to take into account the differences. So I'll be upfront about this. In Haskell, all the code that I'll be showing you in Haskell, that's a runtime code. This is what happens when you run the program, right? Whereas the examples I'll show you in C++ are pure compile time. And at compile time, C++ is a pure functional language, just like Haskell. There's no mutation. You operate on types, so you don't mutate types. In Haskell, you operate on regular data types, on integers, structures, or whatever. Whereas in compile time C++, in metaprogramming, you operate on types. But types have such big structure that you can express so much with types that's plenty. Plus you can use integers to parameterize your templates. So you parameterize your templates with types and integer. Yes?
Wouldn't you say that laziness is another major difference between Haskell and C++ at compile time?
Is it really? I mean,
well,
yeah.
It's definitely not lazy in C++.
Okay, is laziness the difference between Haskell? Haskell is a very lazy language. Okay, it doesn't
lazy, right?
Completely lazy, the laziest of the languages, right? Now I'm not sure what it means to be lazy at compile time. Do you know?
Well, yeah. So in Haskell, you can operate on infinite sequences, for example.
Oh, okay. Gotcha. Mm-hmm.
And if you try to do that in C++, it imperatively, eagerly will run down the sequence and you'll never come back, right?
Right.
The stack of the compiler.
Right, yeah, you blow the compiler, yeah. That's true.
Well, yeah, you can make it lazy. That's true.
You can make it lazy.
Our normal way of doing it isn't.
Okay, so this is the plan for the first. I'll make it 45 minutes. This first part. I'll try. Okay, and then we can have like 5 minutes to stretch, and then continue another 45 minutes, and there will be the next session. Also, I'll divide in 45 minutes. So I'll talk about functions, because we are talking functional language, functions and their corresponding meta functions in C++. I'll talk about lists, which is a rather new thing in C++ OX, because it involves variadic templates. I'll talk about higher order functions, something that is new to runtime C++, but has been there in compile time C++ for quite some time. We'll talk about lambdas and closures, variadic templates, that's about lists, variadic templates, and TPPs, which are template parameter packs. I'll show you list comprehension in C++. I'll talk about continuations at Metaprogramming, and there will be a little bibliography at the end. Here's a teaser. Okay, you are all guys do metaprogramming, so is that something that is understandable at this point, and should I like stop right here and go? Because I'm going to explain this at some point. At the end of the talk, you should be able to understand this. This is a short meta program. Okay, so let's start with functions. So what happened in template metaprogramming is that it was sort of discovered in C++, I think. Somebody just noticed that they can implement a factorial at compile time, and it was like a big discovery, and then this whole area of template metaprogramming started and flourished. But since it wasn't planned in C++, templates were there mostly to support parameterized types, things like containers, parameterized functions maybe, but not for template metaprogramming. So since it was discovered, it's. Did you guys watch these survivor programs on TV, where a guy is on a desert island and with sticks and a bit of plastic bag, he can distill water and do all this kind of stuff. So in C++, this is what template metaprogramming looks like a little bit. Like in Haskell, you do it, the easy way. In C++, you have to go through all these hoops, because it wasn't designed from scratch. It was actually found. So you find these sticks, you find a plastic bag, and you make do. So this is the first program in Haskell. And it shows a lot of things. First of all, it shows an extremely terse syntax. So I'm defining a function, which I call fact, for factorial. And I define it in a mathematical way. Right? So I'm saying factorial of 0, what is it? It's 1, right? So that's a definition of factorial of 0. And then factorial of n, where n is non-zero, because the first case already took care of 0, right? So now n is non-zero. There's a specialization for any n other than 0. It's just n times factorial of n minus 1, right? So it calls itself recursively. That's very. And then you can type fact of 4, and it will give you the result, which I think is 24, is it? Something like that. Now the syntax is very terse. You don't see parentheses, neither when you are defining a function or when you are calling. the fact that I put parentheses after fact here in the second line is because I want to tell Haskell that to first evaluate n minus 1 and then call factorial with it. It's not because I'm putting arguments in parentheses. It's just that Haskell is greedy in getting its argument, so it would think, okay, factorial of n and then minus 1. Okay. So this is this code in C++. It's much more code, really, which is expected, right? And the stuff in red, highlighted in red, this is Haskell. The main difference here is that I had to invert these. So I have two definitions of factorial here. I have two definitions of factorial here, but they are inverted because resolving a function call in Haskell is slightly different than it is in resolving a meta function call in C++. In Haskell, you just look one after another. So you first try factorial of 0, right? Since I'm calling it with 4, that's no match. Okay, so I'm trying the next match, factorial of n. Does 4 match n? Yes. So I go on calculating, right? In C++, it's the best. First of all, the compiler tries to find the best or narrowest match. It doesn't go this first, this next. And the other thing is that it has to see first the general case and then specializations. And yeah, so this is the general case. For any n, I'm defining it as a meta function that returns n times factorial of n minus 1. Now the trick is to implement a function at compile time. You really implement a struct. You just define a data type, and what it returns, it's a member of this struct, which has a special name. For instance, value. I think that's the accepted convention, but it's a convention. Okay, so I know when I call a meta function, I have to access double colon value. Okay, because by convention it has something that's defined as value, and this value has to be a static const int, because only those can be initialized at compile time. So I'm really so this is the initialization of this compile time value, right? And this thing can be executed, can be calculated at compile time. So the compiler just says, okay, I have to initialize this, so I have to evaluate this at compile time. So it goes there and says, okay, so I do this, expand this template. This needs a further expansion and so on, until it hits this specialization here. Okay, until it hits 0. And then it says, okay, but this time I'm calculating factorial of 0, so I'll use the specialization because 0 is a better match for 0 than n, narrower. Okay, so this is a template specialization. Okay, and it's defined as 1. And when I want to call factorial at compile time, right, I call the meta function with integer 4, I just do it and then put double colon value to extract the value. So this is a function call syntax in C++ TMP. So I want you to be able to look at this code and see red. Okay, don't see the black stuff and say, oh, this is a meta function, this is a meta function. Oh, this is calling a meta function. It's just like in Haskell. I want to digress a little bit about types in Haskell, because what I found out that when I'm looking at C++ template metaprogramming code, I usually put a comment there which explains to me what are the types of these in these meta functions. So a meta function is just a template, right? And you don't see any well, you don't see any type in either place, right? However, in Haskell, it doesn't mean that these are not typed variables. Haskell is very strongly typed. It just does type inference for you. So I don't have to put types in there. In C++, I can. Well, in this case, I'm putting an int, okay? So this is type int. But in most cases, you just say class or type name, T, right? That can be anything. It can be any type. So in this way, template metaprogramming is typeless. And of course, you know everything about how types can be introduced into template metaprogramming using concepts, which unfortunately didn't enter into C++ OX. But concepts would be the corresponding typing of meta functions. So in Haskell, Haskell has a multiplicity of types, but the most basic type in Haskell is the function type, right? Because it's a functional language. So function types, when you are writing what type something is, you write a function from type A to type B. You just say A arrow B. That's all. That's a function type. Okay, and type inference in Haskell, how it works. You can actually define the factorial, and then you can ask the interpreter, what type is factorial? And it will type something like this. It will tell you, factorial, well, it's a function type, right, from T to T. But what is T? Is it defined for integers only? Or is it defined for, I don't know, lists? No, it's not defined for a list. You cannot calculate a factorial of a list. Why? Because here is a multiplication sign and here's the subtraction sign. So this type T has to have these two operators defined. So it looks who defines these operators. And it says, okay, it's a type class. It's a class of types that have these two defined. And this class of types is called numbers. Okay? So this says if T is a number, then factorial is of type T goes into T. Okay? And if we had concept in C++, I could do the same. I could say, okay, well, not in this case because this is an int, but in future examples you will see I'm operating on types, right? And when I'm operating on types, I would like to narrow the types and say these are, yes?
Did you have to type the blue line yourself, or is that automatically created by Haskell?
It is automatically created by Haskell, and I can ask Haskell what type have I just defined, right? Or I can put this explicitly in my code, and then Haskell will check it and tell me, was I right or not? This is actually Haskell code, the blue line.
So just the fact that you use the multiplication and subtraction, it reduced the possible types to numbers, right?
Exactly. It inferred the type class.
The num in the parentheses, is that an existing?
It's an existing predefined type class. You can also define your own type classes and so on. So I'm just like with concepts. And you can have instances of your type classes. You can define instances, which is what type map? Concept map, yes. Thank you. Yes?
Can I overload operators? Can I overload operators in Haskell?
Pointers?
Can you overload operators?
Overload operators. This is the way to overload operators. This is the only way in which you can overload operators or overload functions by defining type classes.
But that would mean that I could by different types if I have overloaded operators for types that have a multiply operator.
No.
So the way Haskell works is that a function which includes operators,
Yeah.
operators such as special syntax for functions. A function is defined for one type or one type class, and you cannot
Yes.
overload it to others.
Mm-hmm.
What you can do is say, okay, for this type class, plus is defined.
Mm-hmm.
Plus is defined for the type class num.
Mm-hmm.
So anything that's an instance of num can say, okay, I implement plus this way. But something that is not
Right.
an instance of num cannot define plus.
Yeah, thank you. Okay, another example, predicates. So we have a predicate is 0 in Haskell. So again, is 0 of 0 is true, is 0 of anything else is false. In fact, I could put an underscore instead of x, which matches everything. And if you ask the Haskell what type it is, it will tell you, okay, it's from type class num, again. Why does it know? How does it know that it's num? Because 0 is a number, right? So how does it know it's bool? Well, because true and false are bool. So it can figure it out. Now here's an implementation in C++ of a similar, well, a different predicate is pointer. Okay, and again, it's inverted. This is the specialization. This is the general case. So in general, t is not a pointer. So it returns false. Okay, returns by having a static const, this time Boolean value, false. But there is a specialization that's parameterized by some class type u for u being a pointer. When it matches this pattern u star, it's a pointer, and the specialization then returns true. Okay, and here you have pattern matching. Pattern matching in C++ and in Haskell, they work pretty similar. Okay? Okay, lists. In every functional language, you have functions and you have lists. Lists are the basic data type. Everything else can be built out from lists. Let's say we want to define a function that counts the number of elements in a list. Very simple, right? Now, we define the basic case for an empty list. So these two brackets that looks like a rectangle, these are just two brackets. That's an empty list. The pattern is empty list. When it's empty, the count is 0, right? Otherwise, I can match this pattern head, tail. This is a cons in Haskell. Every list is either empty or it is constructed from its head and another list, which we call tail. So, I mean, I can put any identifier there. I just call it tail in this case, because that expresses what I want. So I'm matching this pattern head, tail. Okay, so when I'm given a list, it will be split into head and tail. And now I can operate on this head separately, on the tail separately. So I say this is okay, 1 for the head, and just count the tail and add these two together, right? And the type signature is a list of t. Why is t a num? Because I have 1 plus. Okay, so it figured out, okay, count must be returning a t, so it must be a list of t.
It's not true. The num restriction is on T1.
Pardon? Oh, no, sorry. Yes. Sorry. Exactly. Num restriction is on the return value because I have 1 plus. I'm returning 1 plus, so it must be a num. Yeah, t is arbitrary, so I can have a list of characters, list of strings, list of anything. Thank you. Same thing, really the same thing in C++ when you have variadic templates. Okay? And this time, I don't have a general case because I either have an empty list or I have to match the complex pattern head and tail. So I don't have a general case, so I have to do a declaration up front. So I'm just declaring that count is a struct, it's a template that takes a variadic argument. So it can take 0, 1, 2, any number of arguments that are types, because I put class here, so they are types. I could put type name there, but it's more typing. So once I have a forward declaration, I can put these specializations in any order. So I will pick the Haskell order. So you see the correspondence. This is an empty list. So count of empty equals 0. Right? Same code, essentially, except for the black stuff, which you are supposed to be blind to by now. And this is head and tail. Okay? So pattern matching in C++. Compile time pattern matching. It works. Okay? If you have a variable number of parameters, you can match this variable number of parameters into two entities. One of them is class head, so it's a type that's the head of this list, and the rest you pack into what is called template parameter pack. So tail is a template parameter pack. This class ... means take whatever is there, pack it into a template parameter pack. And there are very few things that you can do with a template parameter pack. It's probably only one thing, right? Is you can expand it.
Get its size.
Get its size. Okay, yeah. True. Yes?
So the mapping you got here is looks a little bit odd to me, because the Haskell function takes a single argument that is a list, and in this one it seems like you should have wrapped the count in, count of list of head
into a type list,
so that it took just one argument.
Yes, it's not a perfect match in this sense.
It wouldn't be usable in the same contexts.
Right. So for me, a list in template metaprogramming is no, it's not a parameter pack, because the parameter pack is used to match it, right?
Okay.
But it's a variable number of types. Variable number of arguments for me is a list of arguments.
Okay, and you wouldn't put something around it, like a empty struct called list that has to distinguish it as a single logical object? I mean,
I wouldn't. But I know there is an approach in which you actually define something which is a type list, right?
So yeah, what I mean is, if you don't have that, then you can't pass a list and something else following it to a function.
True. It has to be the last thing on the,
Okay.
Yeah, definitely there's a limitation here.
All right.
Okay, so I'm matching head and tail, right? And inside the function, so again, it's 1, it returns 1, plus recursively calls itself. Okay, but now tail is a template parameter pack. It's not a type. It's not a list of types. It's an opaque object. This is how C++ defines it. It's not a type. It's not a variable. It's I don't know what to call it. I call it template parameter pack. The only thing you can do it is you can expand it, and when you expand it, it becomes a variable number of types. Okay. So example, when I'm calling count on 3 arguments, int, char, long, it should return 3, right? So first, this match. Okay, so head becomes int, tail becomes an opaque object that internally has char and long. Okay? So now I'm using this, so I say 1 plus, and I'm calling count with what? I take this opaque object that inside has char and long, and I expand it. So after tail, putting 3 dots after tail means expand it. Okay, so it expands into char and long. So I'm calling count with char and long, a variable number of parameters, this time 2 parameters. Okay, when I call it, this is again split into head, which is char, and into a tail, which is just a 1-element template parameter pack, which obscures the long inside, and so on, until I have an empty list and it matches this specialization. Okay, higher order functions. This is like the meat of functional programming, that functions can be used both as arguments to other functions and they can be returned from other functions. Okay? So this is a nice example, OR combinator. You take 2 functions that are predicates and you just want to combine them into one function that's a predicate. Right? So how do I define it? Okay, so OR combinator has to return a predicate, so it has to return a function, right? A predicate is a function that returns a bool. So in order to return a function, I have to create a lambda, right? And in Haskell, you just create a lambda. You say lambda of x, and this is the syntax. Okay? When you're typing on a regular keyboard, instead of lambda, you put a backslash, which is like a lambda with only 1 leg. Right? So this is definition of this lambda. It takes an x and returns f1 acting on x, because f1 is a predicate, or f2 acting on x. Okay? Now if you're asking me if there's short-circuiting in Haskell, yes, there is short-circuiting in everything Haskell does, because Haskell will never calculate anything that it doesn't need immediately.
Lazy.
Very lazy, yes. So if I combine like these 2 predicates, is 0 and is 1, which you can figure out how it's implemented easily, right? I will get a new predicate that is sort of is 0 or 1, right? And when I act on 2, I'll get false, right? Because it's neither 0 nor 1. I don't really have to put these parentheses there, but I just put them for clarity. Okay, so OR combinator in C++, very easy, right? So you take, so I have to pass functions here, right? So here I will have to pass meta functions, right? So what are meta functions? Meta functions are template parameters. So I'm passing a meta function f1, which is a meta function that takes some type, right? And another meta function called f2, which is a meta function. So it's a template that takes something and returns something else, right? So these are my meta functions as argument to another meta function. Now what I have to return from this OR combinator is again a meta function, right? So how do you return a meta function? Well, it just has to have a member that has some special name, which I just call lambda. I don't know. Is there a way of
Returning a meta function?
Mm-hmm.
Well, I mean, if you take the MPL model, we stuff everything into types.
Mm-hmm.
So you pass meta functions as types as opposed to as templates. And,
Oh, I see.
And,
You do the stuffing. Okay.
and then we return them as types. Also.
Okay. So I went really close to Haskell in here. Okay. So I'm passing template arguments, and I want to return a template. And returning a template means it has to have a member with some special name. I call this lambda. So if you want to access this meta function that's returned by this, you just say : lambda, and that's a meta function.
You couldn't chain this then to another OR combinator.
Yes. You can.
Yes. Yeah. Because what this thing, it's a class member. If I put double call, if I have an OR combinator, and I say : lambda, then this becomes a template. I can pass it to another OR, and so on. Yeah.
What if you wanted to work it with any arity of functions, because it takes two functions arity of one?
You can make a variadic template that.
Can you take a variadic template class as a template parameter?
I think so. I haven't studied, but yeah. Why not? If not in this version of C++, maybe the next one. No, but I think it's in this version. Okay, so I define a lambda, so it's a template of some t, right? So this t corresponds to my x here. Okay, my lambda takes x, this lambda takes t, and what it does with this t, it calls the meta function f1 with this t, calls meta function f2 with this t, extracts the value, that will be the boolean, right? And returns it. So if I can apply OR combinator to, let's say, is_ptr and is_const, which is very easy to define. I extract the lambda from there, and then I call it with, let's say, const int as my type. So t becomes const int. And I extract the value, which is the boolean. In this case, it is const. It's not a pointer, but it's const. So it will return true. Yes?
In our slide, the parentheses in the blue line, are they required?
Oh, I didn't say about the blue line. Oh, okay. Yeah, thank you for asking that. Yeah, this is the type of the OR combinator. So OR combinator, this is a function that takes two arguments, right? In Haskell, a function that takes two arguments is really a function that takes one argument and returns a function that takes the second argument and then returns something. So you just chain it. So the first argument is a function that takes t and returns bool, okay? And I have to put it in parentheses, okay? The second argument is also a predicate, t to bool, and the result, which is like when you have chain of these arrows, the last one is the result of the function. That's how you interpret it. Yeah, you can either interpret it as a function of multiple arguments, or you can interpret it as a function of one argument that returns a function that takes another, and so on. Okay? That's called currying. We'll see more of these weird types later. So yeah, let's get acquainted with them. Higher order functions on lists. So here's a function called all. It takes a predicate and a list, and it just applies this predicate to every element of the list, right? And finds if all elements of the list satisfy this predicate. If any of them doesn't, then it returns and says false, right? So since it's acting on a list, right, I have to pattern match the list. It's either empty, the first case, or I split it into head and tail, right? So if it's head and tail, I apply the predicate to head and end it with a recursive call, right? And I can then call this function all with the predicate is 0 and the list 0, 0, 1, and it will return false, obviously, right? So the same thing in C++.
Why is the empty list return true?
Because it's satisfied in vacuum, right? Mathematically speaking, an empty list satisfies any predicate.
All elements of the list do satisfy it. There just aren't any such elements.
Yeah, all of them, exactly.
Okay, I get it.
All 0 of them.
Everything that's in there, if there were something, it's assumed.
Okay, so in order to do this in C++, since it's a list, I have to start with a declaration up front. So I'm declaring a template that takes a predicate, the template parameter, and a list. Okay? And now I go to specializations. So the first specialization will be for an empty list. It still takes a predicate, right? But the list is empty. There's nothing after the predicate. So it will return true, just like in Haskell. You see, the red code, same as in Haskell. And of course, there's another page of it. I mean, in Haskell, it's written in a few lines, but here you have the page. So I repeat the Haskell definition here so that we see. So this is the specialization when the list is non-empty. So it splits it into head and tail, right? And it calls itself, it applies the predicate to head, ends it with recursive call to all predicate tail. Simple. Yes?
Just want to point something out, that unintuitively, the C++ here is not lazy. So it will instantiate and evaluate predicate for every type in the list.
Ah, okay.
And to make it, you can make it lazy, but it requires making it uglier mechanics.
Yeah. It's true, actually. You know, I mean, this code that's so close to Haskell is not that ugly. You can make it uglier and actually get more into the functionality of Haskell, but not to its syntax, right? So I can either make it not beautiful, I wouldn't call this code beautiful, but sort of, you know, better, nicer. But you can make it ugly and then you can have the functionality of Haskell. Okay, list comprehension, right? I don't know if anybody's seen list comprehension in C++? Yeah? Okay.
If I remember right.
Okay, list comprehension is just sugar in Haskell. I mean, you don't need to do it because you can do it with functions. Okay, but it's a nice way, and it's based on mathematical notation for sets, where you say, I want to construct a set of elements such that. Okay, so here I'm constructing a set of elements that are squares, x times x. Where do I take x from? Well, x is taken from a list 3, 4, 5. Ah, that's the 45 minute. How much slides do I have still? No, not that many. So either we take a 5-minute break here.
Go to the end of your slides.
Yeah?
Yeah, we're all...
Okay, so list comprehension. Using list comprehension, I can, for instance, implement count in a slightly different way. I just take a list and use this to generate all the elements. So x is an element of list. So it goes through all the, so it's like an iterator, goes through all the elements of a list, and for each element of lists of the list, it outputs 1. So it transforms a list of whatever into a list of ones, right? And then I apply sum to it. Sum is a function that will just sum the elements of the list if they are numbers, right? So, yeah. And this is a different, slightly different implementation that I wanted to show because this translates easier to C++. Instead of putting 1 explicitly here, I'm applying a function called 1. A function called 1 just returns 1 for any argument, right? So I'm expanding the list of x's, right? And for every x I call the function 1, which produces number 1. So it's the same code except that it uses a function instead of. So in template metaprogramming, and this is amazing because it fits here. There's no second page to this. Okay? So this is like coming as close to Haskell as possible. So function 1, right? It just returns 1. It's a meta function, it returns 1. Okay? And now I have this count that takes a list. And I don't match this list this time. I don't pattern match it. Could be empty, could be anything. I don't care. I don't have to pattern match it. What I do is I do this. I do pattern expansion. This is very special syntax. You see, the 3 dots here are not after a list. So if I put 3 dots after a list, that would mean, okay, so expand this list, which is a pack, into a variable number of types. And I would call 1 with a variable number of types, I would get an error. Okay? So that's not it. What it is that this whole thing here, before the 3 dots, is a pattern. And list becomes a placeholder for the elements of the list. And when I apply the 3 dots here, these elements pop here, one by one. So I will have 1 of the first element, then I have a 1 of the second element, 1 of the third element, and so on. And this will create me a new list that I will pass to sum. Okay? Sum is a meta function that takes a list of integers and just sums them up. So this is a very, very terse meta function, which I am proud of. So here's this pattern expansion explained a little bit more, but actually I think I did already a good job of explaining it. Say no if I didn't. Okay.
Then how do you put guards on the this comprehension?
Oh. I know, guards. How do you put guards on this comprehension?
I don't think you can do it with that one.
I don't think so, yeah. I was just so happy that I can do anything like this in C++ that I thought, oh my gosh. You know? Okay, and like one of the workhorses of functional programming is this function map that you might know from C++ as transform, right? It takes a list and applies a function to every element of this list and returns a new list. Now this, you would think, okay, well, that should be easy, right? It takes a function to be applied to every element of a list, right? So why don't I just take a pattern, f of list, and 3 dots, right? It will expand list to each element separately and create a list. This doesn't work though. I put typedef here in quotations because I don't know what to put here. Because you cannot return a template parameter pack. And you cannot expand it and then return it because you cannot return a multiple list of multiple types. So this does not work. It's sad, huh?
I think you just get trying to put all of your around it.
Yes, yeah, you can do it with type list, right? Essentially, type list.
Well, it doesn't have to be a const structure anymore, right? It
Mm-hmm.
can just be a struct with a variable number of parameters.
Yeah. Okay, but even this, I can rescue this. Okay, using another mechanism that's used in functional languages called continuation. Yeah, because okay, I cannot return this new list. I can construct this new list. I have syntax to constructing this new list using list comprehension, but I cannot return it. But I can pass it, right? So I can put 3 dots after it, and I can pass it to some other meta function, right? So why don't I have a map with continuation, which takes 3 arguments? It takes the function that I'm applying, the list, and a continuation. A continuation is a function that is to be applied to my list, to my result list. Okay? And I think this is a pretty important thing to understand. So let me explain it really carefully. So first, the implementation of map cont in Haskell, right? So it takes these 3 arguments and it applies the continuation to my result list. And my result list is done using list comprehension. So I take all elements of my list and shove them into F. So I apply F to the first element, second element, third element, and I get a new list. And with this new list, I call my continuation. And my continuation is a function that takes a list and returns some arbitrary type. Okay? So look at the signature of this. This is very important. The blue line at the top shows me that map cont takes 3 arguments and returns some type T2. Okay, the first argument is my continuation. It's a function that takes a list of some T1 and returns T2. Because the result of map cont is whatever my continuation returned, right? So if my continuation returns some type T2, that's what my whole map cont returns, T2. Okay? So this is the continuation parameter. The second is the function that takes T and returns T1. And the third one is my list. And I can translate it word for word into C++, right? So I have continuation, okay, that's a meta function. I have function f that I'm gonna apply to this list. Okay? And look how terse it is. So as before, as I showed you in this previous one, I take this pattern f of list colon colon type, that's my pattern, and I put 3 dots after it. So this placeholder LST will be replaced by all the elements of list one by one. And this will create a list of types, right? And this list of types I pass to my continuation. Okay? Continuation is a variadic template now. So it accepts this list and then I extract the value from this meta function continuation, and that's my return value. Okay? So the use of continuations is pretty important, and I will use them in the second part of my talk. So that's why I wanted you to understand this. Okay, this bibliography. So you can look it up on the internet when these slides are already available. So let's take a 5-minute break. Does it make sense? It doesn't make sense, right? How much time do I have? Half an hour?
4 o'clock was the afternoon break, 4 p.m.
Ah, okay.
For half an hour.
But you probably have to change the tape, right?
Okay.
Or not?
I mean, it's
Okay, but I have half an hour. Okay, so you'll just tell me when to change the tape. So I'll start the second part. Okay, questions?
I don't think I understand what continuation do in your C++ template metaprogram part.
Okay, a continuation is used in this way. My function calculates something, and I don't want to return this something, but I want to continue my calculations with this something as an argument. So continuation is just like the rest of my calculation. So do some calculation for me and then call the continuation. Just say, do the rest of the calculation with this value that I have just calculated. It's just a different way of implementing computations. One is you call a function, it returns a value. With this value, you do the rest of computation, right? And here is you call a function that calculates this value and then calls the function that corresponds to the rest of the calculation. Okay? Yes?
It almost seems like you're turning your list into like a series of function calls with like one element of the list as one argument, and then the rest of the list is another, sort of like with the head and tail from Haskell.
But not when I'm doing it with list comprehension. You see, with list comprehension, I don't split it into head and tail. I'm just saying whatever the list is, apply this function to every element of the list, and that creates a new list. Transform my list using this function, right? So it transforms the list using this function, but what it gets back is it's this template parameter pack, or actually a variadic list, and I cannot return it. So I'm forced to just say, okay, I cannot return it, but I can pass it further. So I'm going to pass it to the rest of the calculation instead of returning it. I'm saying, take the rest of the computations that you wanted to do with this value, right? And just pass it to me as a function. That's what I will call continuation. Just encapsulate all this rest of stuff that you want to do, encapsulate into a function, pass it to me, and I'll call it for you.
Can you show the code again, please?
Yeah. Okay, this was like one of the last slides, right? Okay, this one? So here, do this calculation for me. You get a list. Pass this list to continuation, and I do the rest. Instead of doing calculate this list, return it. And then, with this returned argument, continue. Do the rest of the calculations in your program. Whatever you are doing in your program, whatever is, what you do with this list. Yes?
Is it common syntax in Haskell to have this kind of things? Continuations like this?
Well, this is nothing special. Continuation is just a function. I'm just calling a function with a function.
Yeah, sure, but what do you need?
I don't need to. No. In Haskell, I don't need to. No.
It's because you have to in C++.
Yeah, exactly. I'm using this trick. In Haskell, I can do it this way or that way. It's equivalent. In C++, I can't. Okay, so let me start you on the second part, which is about monads. Anybody knows about monads? Okay, a little bit. Okay, okay. So you guys will help me, huh? No, actually, you know, I this morning I thought I will go through these slides just to remind myself, and I said, I looked at it and gosh, even I don't understand this stuff. Okay. But in the morning, my brain is kind of slow. So I went during the lunch break. I added a few pictures, okay? And I think with these pictures, monads will finally be very easy to understand. That's my hope. Start.
Go ahead, please.
Okay, so monads is something that even many Haskell programmers don't get, at least the beginners. It's like the major block that people get about monads. So it will be really hard to explain it. But why do I even talk about monads? Because I knew a little bit about monads in Haskell and thought, okay, neat, you know, I'm not using Haskell much, so who cares? But then I started studying Proto. Eric tried to explain to me the stuff that they did in Proto, and I thought, okay, so I know Haskell a little bit, right? I'm just gonna explain this thing to myself using Haskell, right? Didn't work, okay? Because what Proto does, it does a bunch of calculations at compile time, and then has this runtime thing. So whatever it produces is actually an object that is run at runtime. So there's like two different worlds. I mean, I know how to do stuff in compile time using Haskell, more or less, right? But I don't know how to add to it the second world of runtime, right? And then it occurred to me, gosh, this is like a state monad, which is also has a very similar structure, that you just do stuff, compose things. It's not compile time, but it's like a separate area of your program where you keep composing stuff. And at the end you get something, you return a function, and then you run this function with state. In this case, in the case of Proto, the state was these x and y and z, these arguments that you pass to your lambda, right? So that's the state. And I thought, no, that won't work. But I tried, and finally I taught myself enough monads that I could translate it into C++. So monads are used in Haskell as a solution to several programming challenges. Because the things that are so easy for us in C++ in functional languages are really, really hard, because they involve things like state, like modifying variables, and things like these. So most functional languages before Haskell, they would just give up and say, okay, this is the functional core of the language, okay, and here if you really want to do some real stuff, okay, you can non-functional thing here in the corner, okay. So do most of your stuff functional, but then if you really need to like do input, output, stuff like this, okay, then here's the little closet with secrets. You could just use them. And the Haskell guys said, no, we have to do it functionally. We have to prove the world that functionally you can do everything. Everything you can do, guys, we can do, and better. Right? So they had to deal with stuff like exceptions, like state, side effects, and of course I/O, input, output. And then there's this other stuff, you know, the proto and mixed compile time runtime programming. That's my personal motivation. So here's the plan. I'll talk about computations versus functions, because what we do in imperative programming is actually called computations, and they are not functions. Then I will give you a pretty much trivial example of the maybe monad, but it shows you the mechanics of monads. It's not that useful in itself. It's useful in Haskell, but probably you wouldn't really want to use it in C++, because in C++ you have something better. Well, better. Okay. Then I'll talk about bind, which is how do you compose these things that are monadic functions. Monadic functions correspond to these computations that are not functions. You turn them into monadic functions. Okay? Return, that's a function that will need explanation, and the do notation, which is the syntactic sugar that makes Haskell look like imperative programs.
Can I make a suggestion, just because you're running short of time, that you just dive in instead of telling us what you're about to tell us? I think everybody's ready to
All right.
see what it is you have to say.
Okay. Teaser.
No, we are. Teaser.
Yeah. Computations versus functions. A lot of computations can be expressed as functions easily. Just give me an argument, I'll calculate something, return the value. Right? And every time you call me with this argument, I'll return the same value. That's the definition of function. Lots of computations are like this. And then a lot of computations are not like this. For instance, there are computations that are not defined for all possible arguments. For some arguments that I say, they just say, no, I cannot. For instance, they return errors or throw exceptions. A function has to be defined for all its arguments. There are non-deterministic ones that return many things, an alternative of things. There are computations that have side effects and state. So if you call it once, it will return a different value than when you call it second time, because it changed state internally. Something it doesn't show as the function has to return the same thing. Here it doesn't. And of course, input output. If you call getChar multiple times, right, it will usually return different chars. Right? So it's not a function, right? GetChar is not a function. I mean, it's something new to C++ programmers probably, but Haskell programmers will always tell you that. So what it turns out is that in order to take these computations that are not functions and put them into functional language, you turn them into functions that return not the original type that your computation was supposed to return, but they return an enriched type. So they just put more stuff into it. Okay? So, like the enriched types for the first case, when you have errors or exceptions, they return this maybe values. So it's like whatever was the computation was returning, I will return 2, except that I will have one more bit saying, is it valid or not? Right? These will be the most interesting for us, the state changing things, because they return actions. And I'm not going to tell you now, because I'm going to explain it fully. Okay, foundation of this stuff is category theory. And I'm just mentioning it. Okay, every monad consists of 3 components, and we'll be talking about these components. One is type constructor. This is how to take a regular type, right, and enrich it. Right? there's bind, which is the composition of these monadic functions. How to compose these new functions that correspond to computations. How to, call this one function and then call the next function with the result of the previous one. If the result of the previous one is this enriched type, right? So I have to take out the value that's inside this enriched type and call it the next function, and so on. And then there's the third component, it's called return, and it has nothing to do with C++ return. It's a function, and it just takes it does for types for values what the type constructor does for types. So it just encapsulates a value into this enriched type. So this is the example of the maybe monad. This is the simplest. Well, it's not the simplest. I mean, there is a trivial empty monad, but maybe monad is like the simplest monad that does something. And here's the motivation in C++. Okay, you have this function method find on strings, right? It finds a character in a string. Okay, and it returns the offset of this character inside a string. And you just want to use it to extract the extension of a file name. So you look for a dot, and then you extract the substring starting from this offset where you found the dot and the length, appropriate length. And it works in most of the cases, right? When most files actually have extension, at least in Windows. But if it doesn't have an extension, this is a disaster, right? Because it returns an offset that is totally invalid. It returns like the, unsigned -1, which is infinity. So when you call substring with infinity, you just get a fault, right? Your program dies a horrible death. And the compiler will not tell you that something is wrong with this code because the special value of error is of the same type as the normal value. It's an unsigned, right? So how is this thing done in Haskell? So here you have a function that is not defined for all values. So this function find is not defined very well for strings that don't have a dot in them, right? So for some strings it's just not very well defined. So you take this computation that we are doing here, and instead of returning an offset, it will return an enriched type called maybe. And this enriched type has an additional bit. So it has this unsigned integer, which it normally returns, plus a bit that says valid, not valid, right? And if it returns this enriched type, you can't just pass this enriched type to substring, because substring doesn't understand what the maybe is, right? It only understands integer. So there is a barrier between these two that forces you to do something, okay? Because just the composing of these two things that I do here, one function returns offset, I use this offset to call the next function. This composition will not work straightforwardly. So in Haskell, you define a new data type called maybe. And you can define this data type for an arbitrary starting type. So you can say maybe of integer or maybe of string.
This is just a parameterized type.
It's just a parameterized type, right. So A is the type parameter here. They call it A or T, lowercase, in Haskell. And this is the data definition. And it just says there are two constructors of this maybe object. One constructor is called nothing, and the other constructor is called just. And this constructor takes a value of type A. Okay. In C++, you would say this is a tagged union. right?
Boost optional.
Boost optional, thank you. Boost optional is maybe. Optional is probably taken from ML, something like that, yeah. So let's talk a little bit more about data types in Haskell. Because unlike data types, data in imperative languages, data in Haskell is not mutable ever. You never mutate anything. So since you don't mutate your data remembers how it was created and with what arguments. So if you created a maybe using the constructor nothing, it will remember that it was constructed as nothing. If you created it using just and passed the value, let's say 7, just 7, it will remember that it was created with just, so it will have a tag just, right, and a value stored of 7.
Is this a side effect of laziness, where the data is actually the expression that creates it?
No, it's just
no.
a tag.
All right.
It's just just a tag, you know. So in order to ask, so you get a piece of data from some other part of your program. Okay, how do you know how it was created? You have to ask it, you know, how were you created? Were you created as nothing or as just? And if just, then what was the original value? And this you do using pattern matching. So you say, do you match this pattern or do you match the other pattern? And if, okay, and the matching is it can either be done as we did pattern matching when defining functions, like you define multiple definitions of the same function using different patterns. You can do it inside a function using case of. So you have some value m, which is of type maybe, and you say case of match this maybe that I get here with different constructors, different possible constructors. So were you created as nothing? If so, then return this expression. If not, maybe you were created with just x. Okay, if you were created with just x, then return this expression. And here I can use the x. It matched the tag and it matched the value. So this m contained some value inside and it was matched with the name x. So here I'm defining a function show maybe. It takes a maybe, right, and it prints it. Oh, it actually turns it into a string. Okay, we don't do I/O yet. So it returns a string nothing in this case, and in this case it returns a string something concatenated with function show, takes an x and turns it into a string. So it's like in Java you have toString. Every object has a toString method. In Haskell you have the show function that takes a type and shows it, turns it into a string. It's not defined for all types, of course, but it's defined for a certain type class of show. Okay, so here's an example. I create x as nothing, and I show maybe x. It prints nothing, right? Like I set y to just 15, and show maybe will say something 15. This is how it works. So this is pattern matching.
I have a question.
Yes?
Is nothing a type, or what is the nothing?
Okay, first of all, it's a type constructor. This is something, it's like a constructor in C++, more or less. It constructs the type maybe with the tag nothing and no value stored.
So we can view the maybe as a union between the nothing and the just a?
It's a tagged union.
Tagged union.
Yeah, it's a tagged union. This is how we implement it in C++. Which is right here, okay? So I define a tag. So this is probably how optional probably is more complicated than this, right? But this is like a simplified optional, right? You have a tag with two values. It's an enumeration, nothing or just. Your maybe, the type constructor for maybe, you know, take any type T and define a new type that contains a value of type T, but this value is only valid if the tag here is just. So if you are using a maybe, you have to look at the tag. If the tag is just, then you can extract the value. Otherwise, don't do that. Okay? You're not really protected from this by any magic like in Haskell, but here in C++ you just have to do this. So if I define a function safe find, and instead of returning an offset, it returns a maybe offset, right? Maybe size D. Then I cannot pass this offset directly to substring because substring does not understand maybe. So what I do is I check the tag for just. If it's just, then I can extract off.value. And here also off.value, right? And this is safer code. Of course, nobody makes me do this. In Haskell, you have to do this. In C++, it just reminds you that maybe you should do this because you have a maybe, yes?
If you use boost variant to implement this, you would have to deal with both cases.
Yeah, okay. Makes sense. It's just that in the other case I do nothing here.
How come, why have you moved into runtime now? I mean, this example is evaluated at runtime.
Yes. Yeah, I'm just, for the purpose of explanation, yeah. Afterwards I'll be doing it at compile time. But this is just showing you know, this is what Haskell does. This is how you can translate it into runtime C++, so that you understand the code. So there is a composition of functions. Okay, so suppose that I have two functions that are of this new special thing that they return maybes. Okay, so I have a function that returns a maybe and a function f. I have another function g that also returns maybe. I have a function h that returns a maybe. Okay, all these functions take some values, not maybes. When I want to execute them one after another, right? So I have to put something between the execution of the first function and the second function that does the checking, right? Error checking. That's what you do. You do error checking after every function, right?
The extraction of the value.
And the extraction of the value. Okay, so both things you have to do. So in order to compose functions of this new enriched type, we'll call them monadic functions, functions that return this enriched type, okay, I have to do some bookkeeping. The black code is the bookkeeping. The red code is what's interesting in this function. So you have a function f of x, it returns a y, call g with this y, it returns a v, call h with this y, v, and returns z, and then finally returns z, right? This is sort of how you look at this. Plus you have all this structure around these things that does the error checking, the ugly stuff. And you see what the proportion is between black and red here? Okay, bookkeeping, a lot of it. But if you want to have a correct program, you have to do this. So, function f of x returns y. Check the tag of y. If it's just, then I can extract value from y, called g. It returns another maybe, and so on. Okay? And the important point is that if any of them returns nothing, right? If f returns nothing, I don't get into this if at all. Right? That's the end for me. In fact, I should have here return something. Oh, okay. It's not a complete example. It's pseudocode. So ideally, I would like to have code like this, right? I'm calling f, it returns y, calling g with y, returns b, calling h, and then returns z. That would be ideal, because now I have only the relevant code, no bookkeeping. So this magic do here would just do the bookkeeping for me. And the question is, can I do this in C++? Can I do this in Haskell? And still have the safety of this code? And the answer in both languages is yes. And it's as simple in either language. So let's go back to Haskell and see about this composition, right? So we want to, we now have these functions that return maybes, okay? These enriched type maybe. And we want to compose them. So I showed you the composition in C++. It requires checking, and then here in Haskell it requires pattern matching. Is it nothing? Is it just, right? And if it's just, that do the rest of the stuff. In Haskell, people think like this. Okay, here's a pattern, right? Every pattern can be expressed as a function. Really. You just have to go one abstraction level above it, you know. It's like one more indirection level in normal programming. In Haskell, it's one more abstraction level. Let's abstract this glue, this red code. Let's abstract it. It's a function. So what does this function do? Well, it takes m as an argument, right? It pattern matches it. If it finds nothing, it returns nothing. But if it finds just, then what does it do? It executes the rest of the code with this value from v1, the v1, from inside the just. Are you trying to say that it's a continuation?
No.
Okay.
I had a question. Can you explain the second line, the black line, let m equals f m in? What does it mean?
Okay, this is a let expression. Let defines a new name for something. So like a variable, but it's not really variable because you don't mutate it. So it says let m be equal to f acting on n. No parentheses in Haskell. This is f acting on n. And in says that this n will be defined in whatever follows. So whatever follows has m defined as the result of acting with f on n. So this is like a local variable, but in Haskell. Okay? So the rest of the computation, hey, that's a continuation, right? It's like, so this function that would encapsulate the red code would take one argument, which is this m, and the second argument, it could take a second argument that's the continuation. And what it does is if m matches nothing, then return nothing. If it matches just, then extract the value from just and call this continuation. The rest of the calculation, right? And now this red code becomes a function. And it's called bind. Okay? Here's my continuation as a lambda. So it's lambda of some v1. Okay? And when it gets v1, it does the rest of the calculation with this v1. So it uses it here. Right? And then this code, of course, here I have a glue also, right? I have case m of this, and this. You do the same with this thing. Okay, this red stuff will be my bind, my function, and will take the continuation. It's continuation within continuation within continuation. So here's the glue abstracted into a function bind. So the red code goes inside bind, and I call it with m, and I call it with a continuation. And the continuation here, it's just lambda that takes v1 and returns all the rest of the code. So I've transformed this code into this code. It's the same thing, okay? But instead of doing this, I'm just turning the rest of the code into a lambda, call it my continuation, and I pass it. This whole thing is an argument to bind. One argument, second argument. This whole thing.
So, what is the order of evaluation in this case? Is f acting on, is f invoked first, followed by g, or followed by h, or is the inverse?
It's lazy.
It's lazy, but when you do call it...
It's lazy, but this continuation cannot be evaluated until v1 is available, right? So yeah, it has to call f first, and then it has to call continuation because there is data dependency between these two. So this is how you do things that require order in Haskell. You put data dependency between them. Before I can do this, I have to calculate that because this depends on that, right? Yes?
Stupid question, probably. Where is f? What is f? What is f? Where did we define f?
What is f? If f is just some monadic function that we define somewhere else. F, g, and h are just three functions that return maybes. Okay?
Go back to okay.
Yeah, they return maybes. They take normal arguments, but they return maybes to just tell the world that they might fail. So I have a bunch of these functions that return maybes, and now I want to chain them, right? I want to do some more complex calculation using these simpler calculations. This is like the basis of all programming, decomposition, right?
Yeah. So why did you make that function also a parameter to the compose? If you can compose f and then everything would be screwed.
Why didn't I make f, g, and h parameters? I could have, yeah. Or they could be just global functions.
Okay.
They often are global functions. You just define a bunch of functions and then you define the composite which uses these functions and so on. Okay, I cannot stop right now because if you lose the track of what I'm saying, I'll lose you, I'm afraid. Right? So let me just do the bind thing. So bind, monadic bind. Now this was a very special pattern for maybe, but this is a totally general thing that you do with monads. Okay? So let me just make sure that you understand this. So a bind, this monadic bind, takes a maybe in this case. So it takes this enriched type, right? Takes a continuation. And what does it return? It returns another maybe, right? In particular, if the first function, if the argument is nothing, that it will return nothing, right? So that's the fallback case, return nothing. If it doesn't fail, it will return just something. So bind returns this enriched type maybe. And here's the definition of bind. And also look at the type signature, okay? So this is translated from what I said there. It takes a maybe of type A, takes a continuation that takes A, this type, okay? And returns maybe of some other type B. Doesn't have to be the same type. I mean, this is a computation that takes an integer and returns a string. It will be turned into a function that takes an integer and returns a maybe string, right? So this is maybe of B, the second argument, and bind returns another maybe, and it's a maybe of this B. So here's the definition of my bind function. M is the maybe, F is the continuation. Case M of, if M is nothing, then return nothing. If it's just V, then call my continuation with V. Done. There's a compact form of this. But yes?
It looks like it would be equally useful to have a maybe where the continuation was only required to return a B and not a maybe B. It would be exactly the same signature except you'd take out that maybe in the middle. And I'm wondering if am I failing to recognize something? Is that maybe important?
Well, no, bind is used to combine monadic functions, so they have to return maybes. If you want to combine with a regular function, then you don't use bind.
You do use bind, but you have to lift the other function into them. So you have to return the other function, which kind of you can. There's basically in the monadic construct there's a function that takes a function from A to B and turns it into a function from A to maybe B, so that you can use it in the.
Okay, yeah, okay. You're right, but I'm thinking of return as taking a value, because it really takes.
It's something like lift, I think.
Oh, okay.
Lifting into the monad.
Mm-hmm. But normally you would do it with return. Return the result of acting with F on something, right?
Well,
you just lift the result. You don't have to lift the function.
No, you lift the function because it's easier than all the time kind of doing a embedding a non-monadic expression, doing a let, and then returning that. It's
okay.
You can do both things.
Yeah, that's a digression though. So this is this cascade of continuation. This is very important to sort of picture in your mind. So I'm acting with F on V. It returns a monadic result, the enriched result. And if it's nothing, I just bypass everything, go to the exit. But if it's just, and I call this lambda, that's my continuation. And this internally, again, calls V1, and it returns this result. I match it. I can return immediately, or I can call another lambda, and so on. And in fact, in Haskell, because you put this sort of stuff in the middle of this, so it's like bind is actually between this and this, they use an infix notation for this. And this is what you can find. If you are looking at Haskell stuff, you'll find this infix operator, right shift infix. You don't have to know this. This is, yeah. And this is the same code that I wrote before, except that now it's using the infix notation for bind. So it binds this with the lambda. Okay. And finally, the return function. This is a trivial thing in this case of maybe, but a return function has to be defined in order to complete the monad. So first element of the monad, there was this type constructor that creates an enriched type. There is bind that uses to combine functions that return enriched types. And finally, there's return, which just takes a regular value and enriches it. Okay? And in this case, enriching a value is just saying, okay, well, it's just V. Right? Okay, let me see what's next. Oh, the do notation. Just for completeness, okay? This code is pretty ugly. Even for, yeah. So there is a special sugar, syntactic sugar to yes?
What is the type of compose? So there's a case when some function call returns nothing. What is that would be a different? What is then the return type of compose?
It's maybe.
So it's maybe or V3, which is not a maybe, or it has to be a maybe.
No, V3 is not a maybe. return v3 is a maybe because that's what
Okay,
does.
because the magic return and that's it.
Yeah, yeah. It enriches it. Yeah. Exactly. Man, I'm gonna finish this, and so the do notation is just syntactic sugar. What is interesting about this is that it looks much more now like what we started with, this magic code, right? I told you this magic do, after which you just write regular code and don't see the maybes, don't see the errors, nothing, you know. This is a special notation which accomplishes this. The whole plumbing of binding is hidden from you. Unfortunately, I won't be able to do this in C++.
But,
Yeah?
so, this is specific to the bind that we just generated, right?
What is specific to bind?
So the bind function object that we created a couple of slides back. So this notation then tells me that it's that bind is that bind is.
Are you asking about do notation? Do notation works for every monad, and every monad defines bind.
Oh, so bind is special.
Yeah. Monad has type constructor, bind, and return. So do notation works for every monad. And this is C++ do notation. Okay? Function compose calls f with v, it returns v1, calls g with v1, returns v2, and finally returns v3. Looks exactly like this, right? Oh, one-to-one correspondence. Except when you call compose, you do this thing, try catch. Okay? So this whole thing is also implemented in C++,